Hello, everyone. Today we'll be presenting our project on crowd congestion prediction, a data-driven approach to tackling traffic challenges focusing on New York City. Our presentation today focuses on starting the solution to crowd congestion, specifically what model to use in tackling a traffic volume prediction problem in major cities.
As far as the content that we will cover, we will first go over a background on the problem, as well as a description of the learning problem, followed by our hypothesis. Then we will go over the data available, and finally, we will go over our experiments and how they were conducted and what results we gathered. The world is experiencing rapid urbanization. By 2050, the UN projects that 6.5 billion people will reside in urban areas, escalating the demand for public services and infrastructure. This rapid growth exacerbates issues like overcrowding and density. Our practical problem addresses the resulting traffic congestion. Highly accurate short-term traffic prediction is essential for transportation agencies and critically for helping residents navigate the city efficiently. The objective is to leverage machine learning to provide forecasts that aid navigation and potentially manage flow.
The core of our work is a supervised learning regression problem. We are acquiring real-world traffic data, generating features, and training a model to output a continuous numerical value, the prediction number of vehicles. Our specific objective is time series forecasting with a focus of predicting the traffic volume in the next 15-minute interval. Our hypothesis driving this experiment was a random forest regressor model can accurately predict traffic congestion levels across New York City roadways. To test this, we compared its performance against other robust regression techniques. The data used, we're utilizing New York City's open data automated traffic volume counts dataset. It includes over 1 million records with traffic counts every 15 minutes. The data covers New York City's boroughs, bridges, roadways, enriched with geospatial information for precise analysis. We began with thorough data cleaning to ensure that the data set was suitable for modeling. First, we combined the separate data and time columns into single standardized date time feature. Next, we addressed the formatting issue in the volume column, where values exceeding 999 were stored with commas. These were cleaned and converted into a proper numeric format. To help facilitate good time series operations, we sorted the entire dataset by segment ID and direction. And finally, we created a target column that defined the volume in the next 15 minutes, as that is how our original data was presented. Once we had cleaned the dataset, we started adding smarter features to help the models predict traffic better. First, we added yes-no flags for weekends and rush hours, namely 7 to 9 a.m. and 4 to 6 p.m. on weekdays. To capture recent traffic trends, we computed a rolling statistic for the mean standard deviation and maximum volume over a 1 hour, 2 hour, and 6 hour window preceding each observation. For the location part, we gave each road segment its usual historical traffic level as a quick reference number and turned categories like boroughs and directions into simple on-off switches with one-hot encoding. All these new features gave the model a more clear picture of both what's happening right now and the bigger traffic trends, making the predictions much more accurate. To test our hypothesis, we selected and trained 3 distinct regression models. A random forest regressor was our primary hypothesis model, like we've already discussed. The reason for this is that tree-based models are robust and it would handle the nonlinear relationship between features like time, rolling means, and location, and traffic volume very well. A gradient boosting regressor was another powerful and simple tree method included to compare performance against the random forest model. And then a ridge regression model was chosen because it was a linear model that served as a good baseline for comparison. The goal of the experiment was to determine which of these models would achieve the highest predictive accuracy for the next 15 minutes of traffic volume. The evaluation of these predictions involved comparing the results across the different models to determine which one was closest to supporting our hypothesis. Specifically, we evaluated the performance using key metrics such as mean absolute error, root mean square error, and the R2 score. These scatter plots give us an immediate visual confirmation of the numerical results. Each point represents a 15-minute interval in the test period, plotting actual versus predicted vehicle volume. The central dashed red line is the line of perfect prediction. We added 2 dashed gray lines defining a plus and minus 6 vehicle tolerance band. Basically, anything inside this band is essentially spot on for operational purposes. And then as we can see here, the random forest plot stands out because the vast majority of the points are tightly clustered around the red line, with very few escaping the gray tolerance zones. Points outside of those gray lines just means that the model was off by more than 6 vehicles. And you can see that the gradient boosting model was a respectable second model. It was very close to the random forest model, but the ridge regression model, which spread was noticeably wider and clearly underperformed.
Zooming into the time dimension, this time series view tracks the first 500 test samples and really shows each model's short-term tracking ability. The blue line is actual traffic volume, and the orange line is the random forest prediction. You can clearly see that the random forest rides almost perfectly on top of the real line, capturing every weekday peak and every weekend dip, and all the subtle fluctuations in between. While gradient boosting and ridge still follow the general trend and capture the periodic peaks and valleys characteristics of New York City traffic, random forest is visibly tighter and more responsive. This confirms that our extensive feature engineering successfully taught the model the underlying temporal patterns. Next, we see the results of the model comparisons. Here in the comparison summary, we can conclude which model performed best. We evaluated the random forest, the gradient boosting, and regression models based on the standard regression metrics discussed earlier. The data confirms that the random forest model achieved the lowest mean absolute error, identifying it as the overall best model for predicting congestion. Specifically, the random forest model achieved a mean absolute error of 10.49 vehicles, indicating that the average error in its prediction was approximately around 10 cars. Furthermore, it yielded a powerful R-squared value of 0.9836, confirming that it accounts for a large majority of the variability within the traffic volume data. This metric summary reinforces our earlier findings that the gradient boosting was a close second, but ultimately, the random forest consistently provided the most accurate and reliable predictions.
And that concludes our presentation. Thank you for listening.